Hello, I'm Joseph Kasser, and welcome to this podcast where the AI team does a deep dive into some application of systems thinking.
Imagine you're building a house, right? You don't just wander onto an empty dirt lot, start nailing random 2x4s together, and just hope a living room magically appears.
I mean, that would be a catastrophic waste of lumber. You need blueprints. You have to understand the physics of the load-bearing walls, the plumbing routing, even the topography of the land before you ever pick up a hammer.
Exactly. Yet, when it comes to creating software, which, essentially runs every critical aspect of our modern world at this point, a massive number of us just start nailing digital boards together.
Right. We just start typing and hope a program appears.
Yeah, and today we're tearing down that just start typing mentality. For this deep dive, we are looking at a resource that treats program design not as some niche coding skill, but as a fundamental liberal arts problem-solving tool.
We're diving deep into the second edition of the textbook How to Design Programs. It's often abbreviated in the community as HTDP. And this is written by Matthias Fellison, Robert Bruce Findler, Matthew Flatt, and Shriram Krishnamurthy, published by MIT Press.
And as part of today's review, we have to highlight a massive detail right up front. The authors actually made this incredibly dense, highly valuable curriculum entirely free to access on the web.
Which is amazing.
It really is. You can find the URL right in the description of this deep dive. Our mission today is to review this book, rate it against the typical programming tutorials out there, and extract its core philosophy.
Because this book makes a pretty bold argument, which is that program design is a skill critical for journalists, accountants, surgeons, and, well, you, the listener.
Right. So to understand why How to Design Programs earns this elite status compared to those standard coding manuals, we first have to look at the massive flaw the authors identify in how programming is traditionally taught.
Let's unpack that. Usually when someone wants to learn to code, they pick up a book titled something like Learn Quick Programming in Python or Master JavaScript in 24 hours.
Oh, yeah, totally.
They focus heavily on whatever language is currently dominating the job market.
And the authors argue that this approach fundamentally sets students up for failure.
Right. Exactly. Because by focusing entirely on the specific syntax of a trendy language, these tutorials completely fail to teach the underlying transferable skills of design. Fashion in programming is extremely short-lived.
Right. The language that runs the web today might be completely obsolete in a decade.
So if you only learn the syntax, you're just back to square one.
I like to think of it like learning a foreign language. The standard tutorial approach is like memorizing a massive dictionary without ever learning the grammar.
That's a great way to put it.
Sure, you know a bunch of words, but you can't construct a meaningful, complex sentence to save your life.
And the book has a brilliant phrase for the outcome of that method. They call the exclamation, "It works," the shortest lie in computing.
Huh. Because getting it to run once doesn't mean it's actually designed.
Exactly. The typical course teaches this tinker until it works approach.
Yeah.
The student writes some messy code, tweaks it randomly until the output looks somewhat correct, yells "it works," and just moves on.
But that single phrase has literally cost people thousands of hours of their lives.
Oh, absolutely. When that code inevitably breaks later, or the parameters change, it is an unreadable, tangled mess. The authors draw a stark contrast here. They say standard programming is like crayon sketches in a diner, whereas systematic program design is like oil paintings in a museum.
Okay, wait, let me push back on that a bit. If I'm a beginner trying to learn, say, C++ or Java, and I miss a single semicolon.
Oh boy.
That's right. The compiler screams at me with 100 lines of gibberish about a segmentation fault.
Yeah.
If this book is teaching rigorous, high-level museum-quality design, doesn't a beginner just get totally crushed by complex error messages before they even get to the theory?
Well, that is the exact problem industrial languages have. They diagnose errors as if the programmer already understands the entire architecture of the language.
Which they don't.
Right. So to solve this, the authors made a really fascinating choice. They created their own sequence of teaching languages specifically tailored for the learning process.
Oh, wow.
Yeah, starting with something called Beginning Student Language, or BSL.
So instead of teaching Python, they teach a language built purely for education.
Exactly. BSL is essentially just pre-LRA. It includes very basic notation for function definitions, function applications, and conditional expressions, which is just a formal way of saying basic if-then decisions.
Gotcha.
Because the language is artificially kept incredibly small, the error messages are actually comprehensible.
So if you make a mistake, The computer speaks to you in terms a middle school math student could understand.
Precisely. It forces the learner to stop hunting for missed semicolons or weird syntax quirks and instead focus entirely on the core principles of design.
Which brings us to the actual methodology they use to paint those museum-quality programs.
Mm.
Because having a simple language is just the canvas, right?
Mm.
The brushstrokes come from their rigorous six-step design recipe.
Yes, the six-step design recipe is the core of this whole thing.
Let's apply this practically, because the book claims this is for non-programmers too.
Mm.
Let's say I'm an accountant building a complex tax bracket calculator.
Yeah.
I don't just start writing algebra.
Right. Under the six-step recipe, step 1 is problem analysis and data definitions. You don't touch any actual math yet. You figure out how to represent real-world information as pure data.
So for the accountant, how do we represent a taxpayer's income? Is it a whole number, a decimal?
Exactly. Once we define the data, step 2 is the signature, purpose statement, and header.
Okay, so I would write down what kind of data the calculator consumes, let's say a dollar amount, and what it produces, which is the tax owed.
Yep.
Then I write a concise, one-sentence summary of what the function actually does.
And notice we still haven't written the logic of the program.
Right.
Step 3 is functional examples. You manually work through what the function should do.
Okay, so I grab a piece of paper and calculate that if the input is $50,000, the output should be $5,000. I do the math myself to prove I understand the goal.
Exactly. Then step 4 is the function template, where you translate your data definitions into an outline. Step 5 is the function definition, where you finally fill in the algebraic gaps. Yeah, finally. And then step 6 is taking those manual examples from step 3 and turning them into automated tests to prove your algebra from step 5 is actually correct.
This process heavily emphasizes creating intermediate products. The authors actually suggest writing these 6 steps on a physical index card.
That trail of breadcrumbs is vital. Imagine a novice programmer gets stuck. In a standard tutorial, they stare at a blank screen, just completely frozen.
We've all been there.
Right. But with the design recipe, an instructor or the student themselves can look at the card and find the exact point of failure.
Yeah.
Did you skip the manual examples? Did you fail to define the data properly?
You always have a concrete intermediate step to fall back on.
Exactly.
I see the massive value in that for learning. But let's look at the real world for a second. Doing this for every single calculation seems impossibly slow.
It sounds like a lot, yeah.
Right. Like if I'm building a massive software suite or even a sprawling financial spreadsheet, I can't stop and outline a 6-step index card for every tiny subcalculation before I move forward. I'd literally never finish the project.
Well, you don't have to write the deep logic immediately. To manage massive projects, the book introduces the concept of the wish list.
I love this concept because it applies to almost any profession.
It really does. When you're designing a complex program, you engage in top-down planning. You write a running list of function headers, just the name, the signature, and the purpose of the tiny functions you realize you're going to need.
That's your wish list.
That's the wish list.
It's like an investigative journalist outlining a massive 10,000-word feature. They are writing the main narrative and realize, oh, they need a section explaining the mayor's complex real estate holdings.
Right.
Instead of stopping the narrative flow to research property records for 3 hours, they just write a header. Wish list. Insert paragraph explaining mayor's real estate impact. Then they keep writing the main story.
You basically delegate the granular work to your future self. Professionals do this because programs or articles or complex spreadsheets are fundamentally written for other people to read.
Or for a future version of yourself who has completely forgotten what you were thinking 6 months ago.
Exactly. Rigorous documentation through a wish list separates a professional product from a messy garage project you just tinkered with until it worked.
So the 6-step recipe and the wish list organize a single static piece of logic beautifully. But how do we scale up? Like, how does the book take us from an algebraic tax calculator to an actual interactive application with moving parts?
The book borrows a concept from the physical sciences called iterative refinement. The authors describe programmers as mini-scientists.
Okay, mini-scientists.
Yeah. A scientist trying to understand the solar system creates an approximate idealized model first. When the predictions don't quite match reality, they revise the model to add more detail, like atmospheric drag or gravitational pull from other planets.
So programmers strip away all the inessential details to solve the core problem first, and then iteratively add the details back in.
Right. And the book uses a fantastic example of building a Space Invaders game to illustrate this. You don't sit down and code the graphics. the scorekeeper, the alien physics, and the player input all at the exact same time.
You'd go crazy.
You start with basic data definitions. You enforce a strict separation between the model and the view.
Let's explain that separation because it seems to be the linchpin of their whole architecture.
Yeah, so the model is the raw mathematical data tracking the state of the world. It's the pure physics. It's the X and Y coordinates of a tank moving along the bottom of the screen, or a UFO descending from the top.
Okay.
It has no idea what a UFO looks like. It only knows its location. The view is entirely separate. It is the rendering logic that takes those coordinates and draws the actual pixels on the screen.
But building a simplified math-only version of a game or a simplified business application kind of feels like doing the work twice. Aren't you just building an ugly prototype only to tear it all down and add the complex visual layers later?
Well, because of that strict separation, adapting to changes is never a teardown. The client, whether that's a paying customer, an editor, or a chief surgeon, will inevitably change their mind.
Oh, always.
They'll look at the Space Invaders game and say, actually, market research says kids hate UFOs. Make it a descending dragon.
And here's where it gets really interesting. If you intertwined your physics logic with your graphics logic, replacing the UFO would break the whole game.
Completely.
The dragon's a different size, so the collision detection breaks, the movement speed feels wrong, you'd have to rewrite the entire program.
But because HTTP teaches you to have single points of control, updating the program takes seconds. You simply swap out the image constant in the view.
Wow.
The model keeps running the exact same math on the exact same coordinates. Iterative refinement means you are building a solid, flexible foundation that welcomes change.
So the Space Invaders game works beautifully using the structural design. The data dictates the shape of the code. What happens when the game needs an artificial intelligence that calculates 1 million possible moves in advance?
Right.
Or what happens when our accountant needs to sort 3 million distinct tax records based on 50 different variables? Your clean structural design suddenly isn't enough. You hit a performance wall.
And this is the moment the book shifts gears from pure structural organization into high-level computer science. It introduces generative recursion, which most people simply call algorithms.
Up until this point, this 6-step recipe has been heavily methodical. But generative recursion requires something more elusive. The authors say it requires a eureka moment.
Yeah, structural design is about breaking a problem down into its immediate, obvious components. Generative recursion requires a leap of insight. You have to look at a complex problem and realize you can solve it by generating a brand new, slightly simpler problem that isn't just a direct physical piece of the original data.
Like the Sierpinski triangle, that famous fractal where a triangle is made of smaller triangles, which are made of smaller triangles.
Yeah.
Or Newton's method for finding the root of a complex math equation.
Exactly.
You can't just arrive at those solutions by following a basic checklist. You need a mathematical insight to generate the next step.
And alongside generative recursion, the book introduces a concept called accumulators. Without accumulators, structurally designed programs often suffer from a loss of knowledge during their computations.
They are constantly recalculating things they should already know.
Right. Accumulators give functions memory.
How does an accumulator actually do that?
Think of a program trying to navigate a massive maze. A standard function walks down a path, hits a dead end, and has to run all the way back to the very beginning of the maze just to remember which branch it originally took.
That sounds incredibly inefficient.
It is. An accumulator is like carrying a clipboard with you through the maze. Every time you make a turn, you write it down on the clipboard. You are accumulating knowledge.
Oh, that makes total sense.
Right. When you hit a dead end, you just look at your clipboard to see your exact path and easily backtrack one step. You never have to return to the starting line.
You carry the knowledge forward. To prove why these high-level concepts matter, the authors do something brilliant. They look at the actual cost of computation. They introduce 2 hypothetical programs that compute the exact same results.
Yeah.
Prog linear and prog square.
This is a pivotal moment for any learner. You have 2 programs. They both yield the exact same correct answer, but their internal architecture is different. The book provides a graph comparing their running times based on the size of the input data.
I want to highlight something really sneaky about the graph the authors provide. On the left side, where the amount of data is tiny, say, sorting 10 tax receipts, the line for prog square is actually lower. It computes the answer faster than the linear program.
Yeah.
But as the amount of data grows to 1,000 receipts or 1 million, the prog square line curves upward aggressively. It spikes into the stratosphere and completely overtakes the straight, steady line of prog linear.
It perfectly illustrates how incredibly dangerous it is to test a system on a tiny dataset, see that it runs fast, and blindly assume it will survive in the real world when the data scales up.
The software works perfectly in the lab, but trashes the moment it's deployed to a million users.
This is the book's gentle introduction to Big O notation, a foundational concept in measuring algorithm efficiency. An expert understands that a structurally designed program might look elegant, but if its performance function operates on the order of n squared steps, like rprog square, it is fundamentally doomed at scale.
Let's break down n squared for a second. It means the time it takes to run the program squares as the data grows. If an accountant sorts 10 receipts, it takes 100 computational steps.
Right.
If they sort 100 receipts, it takes 10,000 steps. If a state government feeds it 1 million tax records, the program doesn't just take longer, it requires 1 trillion steps. The computer essentially freezes for 3 days.
What makes How to Design Programs an elite resource is that it teaches you to evaluate that cost of computation before you ever deploy your software. You learn to mathematically prove that your code won't collapse under its own weight.
So what does this all mean? Let's bring this deep dive home.
When we rate this textbook against the sea of standard programming tutorials on the market, those standard learn syntax fast books might get a 3 out of 10 for long-term value.
Yeah, that's fair.
How to Design Programs earns a 10 out of 10 because it refuses to treat coding as a mechanical skill. It doesn't want you to just memorize a digital dictionary.
It imparts a universal, lifelong cognitive framework for logical thought. And that is the huge takeaway for you listening today. Whether you are an accountant setting up an interconnected financial spreadsheet, a data journalist organizing thousands of local records, or a surgeon mapping out a complex multi-stage procedure, you are essentially programming systems. You take inputs, you apply logic, and you generate outputs.
You don't have to be a software engineer to benefit from this. You can access this entire curriculum for free online today. You can take that 6-step design recipe, the concept of top-down planning with a wish list, and the strategy of iterative refinement and apply them directly to your own workflows to build systems that actually last.
It is an absolute masterclass in organizing your thinking. But before we wrap up, there's one final provocative thought from the authors that we want to leave you with.
In the text, the authors make a deeply profound assertion. They state that computing is simply a natural generalization of grade school arithmetic and algebra.
It's just math, scaled up with variables and logic.
Exactly. And if that is truly the case, why has our society culturally isolated programming? Why do we treat it as this hyper-specialized, mysterious tech skill reserved for geniuses and hoodies?
Right, if it's just an extension of logic and algebra, why aren't we teaching system design alongside basic reading, writing, and arithmetic from day one in elementary school?
It's a great question.
Imagine a world where everyone knows how to read the blueprints. You wouldn't just wander onto an empty lot and start nailing 2x4s together. You'd build something designed to endure. Thanks for joining us on this deep dive. Go check out the book in the description, and we'll catch you next time.
I hope you enjoyed today's deep dive. Why not take a moment and join the discussion in the LinkedIn group Tackling Complex Problems. Take care.